Now, before we get into vectors and all that, we need to go over some trig because we're going to be using a lot of triangles, a lot of triangles. So many triangles. You will not believe how many triangles you're going to be drawing in this class. So it's really important that we have our trig down pat solid. So when we have triangles that are not right triangles, that are triangles of 3 different angles, none of them are 90 degrees, there are 2 ways that we can solve for that. We can use law of sines or we can use law of cosines. And often we're going to have to use a combination of the 2. So our law of sines. Law of sines says that sine of alpha, here's alpha over in our triangle, sine of alpha over the across distance A equals sine of beta, this angle here, sine of beta over the across distance B equals sine of gamma, that angle here, over the across distance C. These can be used in any combination. Usually you're given 2 angles and a side or 2 sides and an angle, and from there you should be able to use these equations to determine the rest of the triangle. Law of cosines is useful when you have 1 angle and 2 sides. Just for this case, 1 angle and 2 sides. Law of cosines says a squared equals b squared plus c squared minus 2bc cosine alpha. So let's take a look at an example of this in practice. Okay, here's an example of a triangle. I want you to go ahead and pause the video and try to solve for the length of side A, gamma, and beta. Okay, so let's take a look at how we would go about solving this. Now, immediately my first thought is, because I have a side angle side, the one that makes the most sense to start with would be law of cosines. So if we look at law of cosines, a squared equals b squared plus c squared minus 2bc cosine alpha. Looking at my triangle, I see that this beta is across from this 10 feet, so I'm going to make this 10 feet my b, and I'm going to make this 14 feet my c, because it's directly across from gamma. So then finally I have A as directly across from my 120, so 120 is angle alpha. If I plug those in, I'm going to get 10 squared plus 14 squared minus 2 times 10 times 14 times cosine of 120. Now we can plug all of that into a calculator, and that's going to spit out A squared equals 436. So we take the square root of each side, and we get that A equals 20.88 feet. Very important. Units are important. We see that all of the lengths of the sides of the triangle are in feet, so our answer A is going to be in feet. Now that we have side A, it's going to be really easy to solve for beta and gamma using law of sines. So if we go ahead, I'm going to go ahead and get rid of this, but write down that our A was 20.88 feet. So we remember that sine of alpha over A equals sine of beta over B. So sine of 120 over our A is 20.88 equals sine beta over our B value was 10. So we multiply the 10 up on this side, and if we plug into the calculator, 10 sine 120 over 20.88 we're going to get that sine beta equals 0.414. Now we'll take the arcsine of that, and we get beta equals 24.5 degrees. Very important that your calculator is in degrees for all of this. We're not really going to be using radians in this class, but there may be special triangle circumstances where, honestly, we're not going to need the calculator at all. But all of your angles are going to be given in degrees, so don't worry about radians. Your calculator is going to stay in degrees this whole class. Okay, so we solved for beta. We got 24.5 degrees, and we can do the exact same process to solve for gamma. I'm going to move all of this out of here. This is also sine gamma over c. So we can say sine 120 over 20.88 as we did before, but now it's sine gamma over 14. So doing our cross multiplication, we get sine gamma equals 0.581. Take the arcsine of that, because the sine to the -1 is usually how it's written on your calculator. Gamma equals 35.5 degrees. So those are our three answers. That's our practice with our law of sines, law of cosines. These will come up, but they will be a little less frequent than using right triangles and right angles. So we'll also go ahead and talk about those. So in a lot of this class, we're going to be breaking down a line into x and y components, and sometimes z components. But a lot of times we're going to be breaking those down into x and y components, and to do that, we're going to be making a lot of right triangles. So just a quick review of the basics. We know the Pythagorean theorem, a squared plus b squared equals c squared, when you're given two lengths and you need to find the third, or you need to backtrack. We also have our basic SOHCAHTOA. SOHCAHTOA, where our sine of theta, here's theta in our triangle over here, sine of theta is opposite over hypotenuse. In this case, it's going to be a over c. Cosine of theta equals adjacent over hypotenuse. In that case, it's b over c. And our tangent theta, which in this case is going to be, well, it's always opposite over adjacent, but in this case, opposite is a and adjacent is b. A over b. So these are super important. They're going to haunt all of your dreams and your nightmares. We're going to use them all the time. Very basic though. I have a feeling you all remember this. You use them all the time in calculus and physics. I just wanted to make sure that we were all on the same page. And as a final point, we are going to have a lot of standard triangles that come up over and over and over again. So when you see these, you should be able to immediately clock them as what they are and what each of the side lengths are. So, for example, one of the standard triangles we see all the time is a 3, 4, 5 triangle. So one side is 3, one side is 4, the hypotenuse is always 5. We see this triangle come up a lot. Another standard triangle that we see come up a lot is the 1, 1 square root of 2 triangle. These are all right triangles. And you'll also see the 5, 12, and 13 triangle come up quite a bit. So these are standard triangles. They always have these. You don't need to worry about angles. Sometimes students will see this 5, 12, and they won't know this is 13. They'll see the 5, 12, and then they get concerned and they start trying to find this angle here, and then they end up with really messy angles, so they're taking sine of this, 47 point blah blah blah, whatever the angle is, when instead they could just be using this nice 5, 12, 13 triangle, just knowing this basic relation. So these will come up a lot. It's just good to be aware of. We'll see more as we start working through some problems with them, but for now it's just good to know.